Hello everybody, Mr. McFarlane here, and we're going to talk today about the Accelerating Cart Lab. So what we're going to do in this lab is basically take a cart, a little toy cart, attach a string to it, hang a weight or a mass on the end of that string, get this system at rest, and then let both objects go. And that's going to take this cart and make it accelerate off the table. Now I'm just going to catch it before it flies off the table so it doesn't break anything, but this car is going to start at rest and pick up speed along the way. Now if you remember, the last lab that we talked about was gliding along at constant velocity. If you remember the displacement versus time graph, that was linear, and there's a horizontal line for velocity. But now, this cart is going to start at rest, and it's going to slowly pick up speed as this weight pulls it with the string. So I'm going to show you that setup here. Alright, so here's the cart that I'm going to use. It's just a toy cart, rolls really nicely. On one end of the cart I attached a string, and on this end of the string I attached a mass, a 1 kilogram mass. Sorry, 500 gram mass, so 0.5 kilograms. Now it's completely arbitrary what I use for the mass, the hanging mass, and for the mass of the cart. Obviously if I use a heavier mass, it's going to accelerate the cart more. But it's kind of arbitrary what I use. As long as I have enough mass to get the cart to actually move, this lab will work great. Now, to collect my data, on the other end of the cart, I taped a long piece of paper, just a long skinny piece of paper, and I want to put this piece of paper underneath an old-fashioned doorbell. One of these things. Now, this old-fashioned doorbell basically is just a little needle that goes up and down. When I turn this on, it's going to go up and down really fast, and it's going to basically leave marks on this piece of paper. I'm going to take this piece of paper, I'm going to weave it underneath the needle, and also on top of that I put some carbon paper. Carbon paper is going to leave indents and also marks of ink on the piece of paper so I can see it better. So when I turn this on, it's going to go and leave these little dings, and the thing is, it's going to be as consistent as possible. There's a certain frequency set with this, and it's going to go as consistent as possible with those marks. Okay? So I want to show you what that sounds like. I'm going to turn this on, and basically as the paper starts here, and then as the cart moves, it's going to pull this paper through. The dots are going to start close together, and they're going to spread out. When I turn this on, that's what you hear. Pleasant sound, right? So basically, like I said, as the paper gets pulled through, this is gonna leave dots on the piece of paper. They're gonna start to close together, and they're gonna spread out. I'm gonna test it out right now. Now, a couple things to note is that I want to make sure that I put the piece of paper underneath the carbon paper. So I weave it in here, and also I want to make sure that I feed it all the way through, so that there's enough tape to go all the way through. So that when the cart falls off the table and I catch it, that there's enough data collected on the piece of paper. So I'm going to feed it all the way through as much as possible, make sure there's no tangles in it, make sure it's nice and straight. And then, it's kind of arbitrary where I start this, as long as there's enough data to collect. And I want to make sure that this hanging mass has enough room so when it gets to the bottom of the floor, there's only a 93 centimeters tall table. When it gets to the floor, that this cart is still accelerating. All right? So I'm going to turn this on, and then I'm going to drop the weight. Now, basically, like I said, the doorbell left some marks on the piece of paper. So I'm going to actually take off this piece of paper. I actually went along and marked the piece of paper afterwards. But I will show you what it looked like. Now, see these little dots here? Not the lines themselves, but the dots. see how the dots start off really close together, and as I move the paper along, those dots get farther and farther apart. Now what I did to make it more easy to see is I made a line after every third dot. So I made a line, and I went 1, 2, 3, marked the third dot, went 1, 2, 3, marked the third dot, went 1, 2, 3, marked the third dot, went 1, 2, 3, marked the third dot. So you can kind of see how those lines are also getting farther and farther apart as I move the piece of paper along. Those lines are covering more and more displacement in the same amount of time. Now, just to kind of prove that the car is accelerating, I take a slow motion video and I set these markers at 10 centimeter increments, and I pause the video at every second so you can see that the cart is indeed traveling farther and farther as time goes on. 3, 2, 1, go! Now if you notice, at about 1 second, the cart traveled about 1 marker in distance. At 2 seconds, it covered 2 more markers almost, and at 3 seconds, it covered about 2.5 markers, maybe 3. So going back to the piece of paper, remember every third dot I made a mark. And so if you notice, I highlighted those marks in nice blue marker for us. And then what I'm going to do is I'm going to go back and I'm going to read the total distance traveled from the starting point, the starting mark, until the very end. For example, that first dot on there is about 0.8 centimeters away from the starting point. The second dot on there is about 2.3 centimeters away from the starting point, etc. And with this data, I'm going to with this information, I'm going to create some data that we can use in our lab. Now, the last thing to think about with this lab are the errors and uncertainties that are embedded with it. Now, if you look back at this part, you can see how the dot timer actually shakes as I let the cart go. One way to alleviate that would be to clamp the dot timer down, but just know that any type of lab you do, there's always going to be some sources of error and uncertainties. And we need to consider that in this lab in particular, because those small errors can add to a bigger error, whether they're in the experiment itself or in measurements that you make along the way. So, there are basically 3 goals of this lab in general, what we're going to try to figure out. One is, what does accelerated motion look like? And we kind of already showed that with the video, but just kind of understanding what acceleration looks like. Number 2, how do we graph accelerated motion? What does the ST graph look like? What's the VT graph look like? What's the AT graph look like? What do those graphs look like, and what's the relationship between the 3? And then finally, how do we account for those small errors or errors and uncertainty in our measurement? How do we account for those? What do they tell us? And what do we do with that information? All right. So with those 3 goals, we should be able to analyze a bunch of different things about this cool lab, and hopefully we can get things rolling.